Good morning, everyone. How are you today? Good. お元気ですか皆さん、お元気ですかわからない大丈夫ですよ Okay, so I think we have less students than I expected. Where are they? Where are they? On the way to the classroom. Okay, good. Anyway, I think we don't have enough time to wait. So let's have a quick review, recall about what we have learned last week. Last week, this is important. We know that in order to get, in order to analyze data, the easy way is that to make the data become a straight line, right? So if you have a straight line, and you can find out equation. For example, you can use, if you have a straight line, you can use a graphical interpolation to find a straight line, right? Okay. And also, you can have a 2-point linear interpolation. You pick up the 2 points, and you plot the line. You get the answer. You get A and B. Okay, and or you want to do a mathematical method like linear regression or something. That's mathematical method. So actually, you have 3 methods to realize the equation of this line. Okay, and then if you don't have a straight line with your data, I try to make it as a straight line, right? I remember I give you 4 examples. 4 examples. Okay, so that 4 examples you can make the fitting you can fit in the non-linear data to make it become linear. Okay, and then finally, last week we talked about in the chapter 2 we talk about log plot, right? Logarithmic coordinates. Okay, that means that for the coordinates you have a rectangular coordinates, right? X and y axis, y axis and x axis, you have rectangular coordinates, and you also have a log plot. This is what we call log plot, right? And when are we going to use this log plot? When we have power law. Power law is y equal to a times b power x. This is what we call power law. When you have an equation like this, and you use the log plot, then you will find out that the data will become one straight line. So as a result, you can find out A and B here. You can find out A, where's my cursor? You can find out A and B. So once you find out A and B here, and then let me, you have straight line, so you will be able to find out A and B using this straight line, 2 points. You can use graphical exploration. You can use 2 points, and you can use curve fitting. But in your midterm exam, I suggest you to use 2-point linear interpolation. Okay, I suggest, but you can do anything you want as long as you give me the right answer, right? Okay, so and then next one is what we call semi-log plot. Semi-log plot this is rectangular scale. From here this is rectangular scale, and this is what log scale. So that's why we call semi-plot. Okay, so what kind of function apply to this semi-log plot? Exponential function. Exponential function is y equal to a times b power b times x. If you log in both sides, you will find out this is a semi-log plot. I hope you go home and read this. Normally you need to spend 9 hours per week to study this course because I give you 3 hours lecture, right, per week. So basically, you need to spend 9 hours to study this course. If you don't, you might get not enough scores for to pass this course. But anyway, the choice is yours. Okay, this is chapter 2. So that's what we learned from the chapters 2. And the chapter 3, we talk about the processes and the process variables, right? Okay, so where are we? So basic in first this is 3.3. Let's go to the the first one is that we start to learn the process, right? Process, and we know the mass and volume. And then if we have a mass divided by time, what is this called? Mass divided by time. This is what we call mass flow rate, right? Mass flow rate. If the volume divided by time, that's what we call volumetric flow rate. Hope you remember. Hope you remember. Okay, so what's the conversion factor between volumetric flow rate and the mass flow rate? What's the conversion factor? If I say, well, if you do experiment and you got a volumetric flow rate, I say, please change volumetric flow rate to mass flow rate. Can you do that for me? Yes, you can. Conversion factor is density, right? As long as you know the density of the fluid, then it'll be easier for you to get the answer, right? Okay, so this is the one we learned. So important thing is you need to know the definition of mass, volume. Volume will be varied by temperature. Temperature increase, normally volume increase. Okay, and then density will decrease. And then you know that there's what we call specific volume and specific gravity. What's the definition? And the thermal expansion, because temperature is related, density is related to temperature. Right. So in the section 3.2, we talk about flow rate. I think I already discussed this about. We already learned about this, and this is the tool to measure the flow rate. And this is called what? This is called what? Rotameter. Rotameter. R-O-T-A-M-E-T-R. Rotameter. So I'm sure you know that in your midterm exam, this is 100%. This equation, this question will be 100% in your midterm exam paper. So no matter you like it or not, you need to remember this. Okay, you need to tell me this for information, and you need to draw a picture like this for me, and let me understand. You understand this, and you'll get scores. Okay, and also I want you to give me a explanation about these sentences. Okay, you can write in Chinese, you can write in English, you can write in Japanese as you like. I'm sorry, I don't understand Korean, so just read this language. Okay, so that's it. That's what we learned about this. So in the section 3.3, I think basically we need to know how to express the chemical composition. And that's what we are going to start today. So if you have a mixture of A, B, C, D, E components, how are you going to express how many amount of A in this mixture, how many B amount of this, how many amount of B in this mixture? Okay, so basically before we start, we need to know the moles and the molecular weight. I'll go through this very quick. I'm sure you understand atomic weight, right? Atomic weight. And how about molecular weight? If you understand atomic weight, of course you understand molecular weight. Okay, and then moles. So moles of the species in the amount of that species whose mass is numerically equal to its molecular weight. I'm sure you understand this. You learn this when you are in junior high school. Okay, so let's skip this. So if I give you a common monoxide molecular weight, you have to count from atomic weight, right? So please remember this, and you understand now 1 mole is about 6.02 times 10 to 23rd atoms or molecules. This is what we call 1 mole. Right, so this is conversion. So if you want to convert moles and the mass, what's the conversion factor? Molecular weight or atomic weight? Okay, molecular weight or atomic weight. However, I'm sure now you understand. If you want to know what is the molar flow rate, when we learn mass flow rate, volumetric flow rate, and there's another flow rate called molar flow rate. And the conversion factor is what? Conversion factor between mass flow rate and molar flow rate is atomic weight or molecular weight. Okay? So this is example. Very easy, so I don't want to waste your time. If you have 100 grams of carbon dioxide, how can you change to, it's equal to how many pound per mass moles of carbon dioxide? Conversion factor, right? You just put conversion factor in, you will get an answer. Again, I don't want to waste your time, so please do the calculation this by yourself. Okay, this is the answer. So, right. So this is important here. I want to tell you is that now you have 3 flow rates. First one, mass flow rate. Second, volumetric flow rate. Third, molar flow rate. So it's all mass divided by time, volume divided by time, and mole divided by time. So how are these 3 going to change to each other? If I say that, please change, if we have a rotameter here, for example, right? Where is that? If we have a rotameter here, and you got a data, you know the flow, you know the volumetric flow rate, you measure the volumetric flow rate. I say that, well, don't tell me the volumetric flow rate, tell me the mass flow rate or molar flow rate. So you understand that from the volumetric flow rate to mass flow rate, the conversion factor is density, right? So you will get the answer of mass flow rate. So when you want to convert the mass flow rate to the molar flow rate, the conversion factor is what? It's molecular weight or atomic weight. Okay, so from here to here, density. From here to here, molecular weight or atomic weight. Right, these are the example. Please do this by yourself. I already get your answer, so I'm sure you can you can do the calculation by yourself. So the 3.3 is that the moles and the molecular weight. Okay, the section 3.3b is mass, molar fraction, mass and the molar fractions, and average molar weight. This is easy, so I think it's very easy, right? So once you found the fraction, what does this information tell you? This is a dimensionless quantity, right? Because it's mass divided by mass, so you don't have unit, so you don't have dimension. So this is what we call dimensionless quantity. Okay, again, for the molar fraction, this is also the dimensionless quantity, and this also tell you how do you express the amount of A in the mixture. Okay, this amount of B in the mixture, you can use this mass fraction or molar fraction to express the amount of the species. Right, so example 3.3-2, this is easy, so please read this by yourself, and these are the answers. Right. And I think I will skip this. This is very easy. So let's move this. Okay, so how about average molecular weight? I'm sure, again, you know that. If you have a fraction and you have m over bar means what? Over bar means what? Average. Remember, when we talk about this in chapter 2, if you have something over bar, that means this average, right? So you have a fraction A times molecular weight A. You have fraction B times molecular weight B, blah, blah, blah. So in the end, you have a summation, right? Yi times Mi. That's it. Piece of cake. Again, this is a calculation. Right, this is 3.3b, mass flow, molar fractions and average molecular weight. I'm sure you all know this already. Right. So next is 3.3c. Apart from fraction to describe the amount of the species in the mixture, what else? What kind of expression we can use? And this is what we call composition. Apart from the composition, and we have another way to describe, we call concentration. Okay, concentration. So these are the 5 definitions in this section. I don't want you to remember all of this, but the last one you need to remember, and I'm sure you already know what is the definition of the last one. When you pass your university entrance exam, I'm sure you know this already. So the first one is called mass fraction of A. So mass fraction of A is that mass of A divided by what? Divided by mass of A times mass of B. This is the example of A, the mixture of A and B. So if you have a mixture of A, B, C, D, E, F, G, then here you will be A, B, C, D, E, F, G, right? Mass of A, B, C, D, E, F, G. How about the volumetric fraction? This is the volume divided by volume A plus volume B. How about the concentration of A? So we don't talk about dimensionless quantity. How about mass concentration? This is concentration of A. So if this concentration is mass A divided by what? Divided by volume. Divided by volume. So if you in the future, if you find something concentration, you might think, well, if you have something divided by volume, divided by volume. So how about molar concentration of A? So if you have an example of mass concentration, I'm sure you know that you know how to describe molar concentration of A. That will be what? Mole of A divided by what? Value of A plus B, right? Value of A plus B. Okay, so please remember this. And the last one is called molarity. Molarity is that the gram moles, okay, and then divided by what? Liter. This is what we know. We use capital M, right? Capital M to represent the definition of molarity. Okay, right. Okay, this is one of the example. Please do this by yourself. So here is the page 26 in this section. I want you to practice this. Okay, so mass flow rate, molar flow rate, and volumetric flow rate. I'm sure. I hope you can you learn this and how you do the practice. That will be easier for. That will be important for you to learn this. So as long as I give you the specific gravity of the sulfuric, right? And also I give you the density of the sulfuric acid, right? So the density and also the flow rate and the molecular weight. Molecular weight. Okay, so that's it. So next important part is this 3.3D. I'm sure you heard about you have heard ppm and ppb. So what's the definition of ppm and ppb? So ppm is stand for parts per million. ppb is stand for parts per billion. So as long as you know what's the definition of million and billion, then it will be easier for you. It will be easier for you to know that the definition and the descriptions. So why we need to use ppm or ppb? This is very similar to the scientific notation. When you have a very small number, and you can use scientific notation. But here, when you use scientific notation, That's the that you need to have with dimension, with units. But when you have a very small, when you want to describe very small amount without dimension, and this is the one of the method to use. For example, if you have a very, very small amount of the object in some place in a solution, you use ppm or ppb. So ppm is stand for parts per million parts, parts per million. So it's yi times what? 10 to 6. Is one. For example, if this is 1 ppm, that means what? You have 1 out of 1 times 10 to 6. That means the concentration is very, very small. Okay? And ppb is the parts per billion. So if you have 1 ppb, that means what? You have 1 out of 10 to 9. In Chinese, in Mandarin, 10亿分之一, right? 百万分之一. Okay. Did this definition tell you the units or dimension? No, right? So actually, this is a dimensionless. So when you talk about ppm or ppb, this is a dimensionless quantity. Okay, I'm going to give you an example very soon. What does that mean? There's no unit. So this is kind of concept of fraction. Okay, 1 out of how many? 1 out of 10 to 6 or 1 out of 10 to 9. So once you have something in liquid and you want to describe in ppm or ppb, so normally we use what? We use mass because we don't use volume. Why? Because volume will change because of time. When time change, when temperature change, not time. I beg your pardon. When temperature change, volume change. So you don't want to use volume to express the concentration. What you can use is mass. Okay, so in the liquid phase, you use mass ratios usually. So if I have 5 ppm, that means what? You have 5 grams, for example, 5 grams out of 10 to 6 grams. Okay, so this is dimensionless quantity. How about gas? Can you use gram to express some substance or object in the gas phase? No, you cannot use gram. Have you used gram to describe some? Have you used gram to describe air, carbon dioxide, nitrogen, oxygen? No, you don't. So what you want to use is what? Mole ratios. Okay, so remember, generally speaking, in gas phase you use mole to describe ppm or ppb. In liquid phase you use mass to describe ppm or ppb. For example, how many? I give you an example here. So this is one of the example. In the power station, around the power station, the air contains 15 ppm sulfur dioxide. What does this mean? What's the 15 ppm means? Means 15 ppm gram or 15 ppm mole. Which one? So is that 15 ppm 15 mole out of 10 to 6 mole sulfur dioxide, or 15 gram out of 10 to 6 grams sulfur dioxide? Which one? Mole, right? Right, because you want to describe sulfur dioxide in gas phase and you use mole instead of gram. Vice versa. If you want to describe something in a liquid, in the water, or in liquid phase, you use gram instead of mole. Okay? Right. In the past, I will ask you to give me the definition of ppm or ppb in the past, but I don't know this in your midterm exam, but I don't know. Probably the chance is about 50-50. So I want you to remember what's the definition of ppm or ppb and ppb. Right, so this is summary, okay? You need to know the composition, you need to know the concentration. You know, composition, you need to know the concentration. Right. So now let's move to the section 3.4. Right, these are chapter 2 and chapter 3 are very easy. So I go very fast. Please work with me and we can go through this easily. Okay, since we only have 16 weeks, right? Before we have 18 weeks, right? Now we only have 16 weeks. So please work with me. Let's fly with the lecture, okay? Right, so now as section 3.4, pressure. So there are two terms here in 3.4a. The first one is called fluid pressure. The second one is called hydrostatic head. Hydrostatic head. So what's the definition of pressure? Pressure is exerted by particles coalesced inside a closed container. So this is what we call pressure. Okay, so this particle will hit the walls and the wall got heated. And so there's a force. And if you have force and you have an area, the force divided by area, that means the definition, that's the definition of the pressure. So if I say that, well, there's no any particle or there's no molecules inside this chamber. So what's the pressure inside? Pressure is zero, absolutely zero. This is not going to happen. It's like absolutely 0 Kelvin. This is not going to happen. Okay? It always has some gas inside the chamber. The temperature is not, you always have a temperature. The molecule always move. So it's very difficult to reach 0 Kelvin or 0 pressure. So the definition of a pressure is a pressure equal to force divided by area. I'm sure you all know this. So for SI system, we use Newton per square meter. We call it Pascal, PA. CGS is dyne per square centimeter. We call bar. For American engineering system, we use pound force divided by square feet. So we use this PSI. PSI is the pound per square inch. Okay, PSI is equal to pound per square inch. Okay, so you might say, well, Professor, normally I use ATM. You know, you go to convenience store, you have ATM. Oh, this is not ATM we are talking about. This ATM we are talking about is a pressure, right? So anyway, we are going to have a table for you later. So what is the fluid pressure? Fluid pressure means that when you have fluid, it doesn't matter it's water or air, pass through a chamber, and then water will come out. Right? If you have water go through or go up or go down, and if you drill a hole here, the water will come out. And in order to stop this water to come out, you need a force. And of course, you have area. This is called fluid pressure. Fluid pressure. So it's kind of dynamic. You know, the fluid is flowing. Okay? So this is called fluid pressure. Again, it doesn't matter you have a pipe which is vertical or horizontal. As long as you have a hole and the water or air come out, you want to stop it. And this is pressure is F divided by area. Force divided by area. The second term is called hydrostatic pressure. Instead of the fluid which is flowing and there's no flow, water doesn't flow, it's steady state here. And then this is called hydrostatic pressure. Hydrostatic pressure, I'm sure you all know this. Underneath, on the bottom of the water, you have a pressure here. The pressure will be atmospheric pressure, P0, plus what? The pressure in the water, right? So how do you calculate the pressure of the water? Rho GH, right? I'm sure you know this. Rho is what? Density. G is gravity. H is what? The height, right? Height. Right, okay, so this is P equal to P0 plus rho GH. And this is what we call hydrostatic pressure. So how are we going to describe the pressure? So this is called atmospheric pressure. When we stay here, we under a pressure from the air, from the sky, from very far sky, very far away molecular or very far away of the air and hit us, and we got pressure. This is what normally we call 1 atm. For for American engineering system, we use pound per square inch, right? ATM equal to 14.7 psi. Okay, and also equal to what? 760 millimeter mercury. That means if you have a 76 centimeter mercury, that will be equal to what? 1 atm. 1 atm, 1 atmospheric pressure. And this is what we call torr. Using instead of PSM millimeter mercury, we use torr instead. Okay, so you might say, wow, Professor, something wrong, because the unit of PSI is force divided by area. But this is meter. This is the dimension of this is the length. Is the length, right? So this is the dimension of this PSI is pressure, but this is not pressure, dimension of pressure. This is dimension of length. So can we write it equal? No, we cannot. But this also represents the pressure. So in the past or now, we use, that's what we call head. Okay, head is also can express the pressure. Okay, so for example, 14.7 psi is equal to 76 centimeters of mercury. And you know the density of mercury, right? So you can use rho GH, right? So you just know that rho is the density, which is a constant. G is the gravity, which is a constant. So you can use H to represent the pressure. That's why we call head. Okay, but I want you to make sure that the unit or the dimension of PSI is different from the dimension of this head, dimension of the head. Okay. So this is one of example using millimeter mercury to represent this number. Can you do that for me? Wow, rho GH, right? Rho GH. So you put this here, and you put rho GH here, and you got pH, H here. I don't want to waste your time, so please practice this by yourself. So this is the pressure unit. When I was a student, everybody got one card of this, because you need to know what's the definition of the pressure. They are SI system, GGS system, American engineering system. You have millimeter mercury. You have standard atmosphere. So you need to know how to do the conversion. And if you have a calculator, of course, you can do this. But when I was a student, everybody has a card for this. But now you don't. You just Google, right? Thanks for the computer. Thanks for the wonderful internet or artificial intelligence, AI, right? So you even can ask ChatGPT to tell you the answer. You don't even need to type, right? Okay, so but here just for your information, if you want to do the conversion of Pascal, bar, technical atmosphere, standard atmosphere, torr, pound per square inch, this is the table. So for example, no, what we always know is that standard atmosphere we call what? 1 atm. That's what we are. This is the environment we are having, right? The 1 atm. So 1 atm is equal to what? 760 millimeter mercury. That's what we call torr. So you need to know the definition of torr. It's millimeter mercury. Okay, and 1 atm is equal to what? 14.7. You just remember 17.7 torr. Sorry, 17.7. Sorry, 14.7 psi, pound per square inch, and it's equal to what? 1.013 CGS, and it's equal to what? 1.013 times 10 to 5th SI, par. This is bar, right? This is Pascal. Sorry, I make a mistake here. Okay, so please remember this by yourself. No, you don't need to remember. Just know that you need to do the conversion using this table. But basic knowledge is this. 1 atm, if I ask you 1 atm equal to how many psi, then you might think that, wow, 14.7. Okay, how many torrs? 760 millimeter mercury, or 760 torr, something like this. Right, so this is an example, the pressure below the surface of the solid fluids. You have atmospheric water, you use water as a unit, right? So H2O here, 14.4 meter. You don't use millimeter mercury, use water. So the head will be different. And you have 30 meters of water here. So if I'm sure you can find out the pressure in this point. Right. So 3.4b is that atmospheric pressure and absolute pressure and the gauge pressure. So I want you to remember these three terms. But of course, I'm sure you already know the first one, atmospheric pressure. So let's have a definition of atmospheric pressure. What is atmospheric pressure? This is our planet. This is Earth, right? So when we have a sea, so we have some air surrounding this planet, this Earth, right? And out of this dashed line here, there's no air in this place. Why? Because the gravity is not strong enough to attract molecules or gas reach to this area, right? Because of gravity. So you have a layer of these airs surrounding this sphere. So out of this dashed line, the pressure is 0 because there's no air, there's no gas, right? So this is height. And then up here, this is called sea level. We use sea level as a standard. And then the sea level is equal to what? Low GH. That's what we learned, low GH. So for the low GH, and it's about 760 millimeter mercury. Okay? And that will be 1 atm. 1 atm. So you might say, well, Professor, so if this is sea level, this is 1 atm, if I stay higher, that means what? Pressure will be less, right? Because this you use low GH. So if the height is less than height is less than h, the pressure will be less. That's why when you are in a high mountain, the pressure is less, right? You cannot suck enough air into your lung because the concentration of air is not high enough as you have at the sea level. So this is sea level is 1 atm. This is height, right? If you go to Denver, Denver is where? Denver is in the United States. Okay, the height is about, well, let's say 2,000. So the pressure will be 0.83 atm because you don't have because you are a little bit higher. So you have less air, okay, to get the pressure. And once you go up higher and higher, like Bolivia, even higher, so pressure is less. It's 0.066, 0.66 atm. Even you go further, that'll be 0.35 atm. Okay, until you go up to the space, pressure is zero. Well, I shouldn't say absolutely zero. It's reached to zero. Right. So next is absolute pressure and the gauge pressure. So what is absolute pressure? As absolute pressure means what? The pressure is zero. Zero. So there is no air, no gas at all. So we use PABS equal to 0 millimeter mercury or 0 Pascal. PSI. A is stand for what? Absolute. A is stand for absolute. You might see PSIG. G stand for gauge. G stand for gauge. So this is the pressure gauge, which is the tool to measure the pressure. So as you can see, the unit of this pressure gauge is PSIA. A stands for what? Absolute. So if this indicator go to zero, that means what? This is absolute zero pressure. Excuse me. Right. So if the indicator go to the 14.7, what does this mean? This is atmospheric pressure. Right. So how about gauge pressure? Gauge pressure is that it's not absolute. It's related to the atmospheric. What does that mean? So if the gauge pressure go to 1 atm, the gauge pressure indicator of gauge pressure go to what? 0 millimeter mercury. So if you have two tools to measure the pressure, and one tell you PSIA, one tell you PSIG, you need to know the definition of PSIA and PSIG. So if one atmospheric pressure in gauge pressure, gauge in the gauge pressure gauge in the gauge pressure gauge, actually it's called Pudong gauge, and then the indicator go to 0. Does this confuse you? This is easy, but I'm sure I'll give you a table, a chart, which is figures will let you understand. So if the pressure is if the atmospheric if the chamber is in a vacuum condition, which is no pressure, so the pressure gauge, the indicator will go to the 0 here. The indicator of the pressure will go to 0 here. So that will be minus 760 millimeter mercury. So you have two types of gauge. One is to measure absolute pressure. One is to measure the gauge pressure. So if I show you something like this, and you will be able to find out this is called gauge pressure, because when indicator go to 0 and there's no measurement of the pressure, then you know that this is indication of the atmospheric pressure. And so this is called gauge pressure. So you can go to -1, right? Minus means what? Minus 760 millimeter mercury. If this goes 1 here, that means absolute pressure is 2 atm. Ladies and gentlemen, please remember this equation. P absolute equal to P gauge plus P atmospheric. Right? So if I say that I have a gauge, let me show you a gauge. We call Pudong gauge. this is the one, and I measure nothing. You know, there's nothing, right? And if the indicator go to 0, what does that mean? And now it's 1 atm, right? So why indicator go to 0? Because this gauge is measure gauge pressure instead of absolute pressure. Okay, if now indicator go to 1, I measure nothing, right? I measure there's no pipe connected. So this is so if the indicator go to 1, that means this is a gauge to measure absolute pressure. Okay, so the important thing is absolute pressure equal to gauge pressure plus atmospheric pressure. So if you don't understand, this is the figures today you understand. So first of all, you have absolute 0 pressure, and you have atmospheric pressure, and you have the pressure above atmospheric pressure, and of course this is below. So you have the atmospheric pressure here, this is above, this is below. So once you have gauge, this is called gauge. This is Bourdon gauge. I'll tell you what's if you have a Bourdon gauge and measure the absolute pressure, that means it go to 0 here. That means what? You have absolute pressure, which is from here go up here, and from here go up here. Okay, so you will go up, go up. I think I made a mistake. Okay, so this is go up, and then if you have a gauge pressure, this is gauge pressure. Okay, this is absolute pressure. So absolute pressure goes up, goes up, goes up, goes up, and gauge pressure, this one goes here and go up here, and this is called gauge pressure. Okay. You might say, well, Professor, what is barometric pressure? You know, barometric pressure is, we call it the atmospheric pressure. Okay, this is a special term, so you don't need to remember this. Right, so once we know the definition of pressure, and then now we need to know what's the tool to measure the fluid. And this is what we are going to learn, and there are tools to measure the pressure. Right, so now let's find out how to measure the pressure. So what are you going to measure the pressure? What kind of tools you want to use? So you can find out from this Peric Engineering Handbooks, Engineer's Handbook. This is I told you this is the Bible. This is the Bible, right? This is the Bible for the chemical engineers. But you don't need this Bible anymore. You just get it from internet. So this is the first one, which is the most easy and most common one we use. It's called elastic element measures. We call it Bourdon gauge. Ladies and gentlemen, this will be 100% in your midterm exam. Okay, Bourdon gauge. The second one is called liquid column measure. We call it marometer. Okay. The third one, you use electrical measure. Okay, this mechanical measure and the liquid, and this is electrical measure. And you can have a strength gauge. You can have piezo-resistive transducer. You can have piezo-electric transducer. But we don't have time to introduce this, but this is important. So we only introduce this one. We call it Bourdon gauge or Bourdon tube. So this is what we call Bourdon gauge. As you know that, as you see something from here like this. So this is the indicator. This is the indicator here. And then you can know that this is 50, 100, 150. This is reading, right? This is reading. And then in order to know what's the unit or the dimension, you need to find this is what the unit here. It's called millibar. So if the indicator go to here, 50, you know it's 50 millibar, right? Okay, and then you have minus and plus, and this is only plus. Okay, so what is Bourdon gauge? So if you open the case, you will see something like this in the front. And if you take a look of the back, you will see something like this. This is a kind of tube, or called Bourdon tube. Bourdon tube. Okay, and this is gas input. We have gas going from here. You can suck the air out. You can put the air in. So if you put the air in, the pressure will increase. If you suck the air out, and this integrator go to this way, and the pressure goes dropped. Okay, so how does this work? How does this work? So this is how it looks like. Is that the pressure inlet from here, and you have a tube, what we call Bourdon tube. It's a kind of flat, curved tube. This is sealed. This is open. This is open to let air go in or air come out, or the pressure go in, pressure come out. It cannot. It can be air. It can be air. It can be nitrogen. It can be oxygen. It can be water. Okay, and you have this part sealed. Okay, end place, and you have a wire link to the gears. This is called sector gear. This is pinion gear. Okay, this is pointer indicator. This scale. So as you know, if I get a pressure to this tube, what happens? If I get a pressure to this tube will go this way or go down this way. Which one? Which one? You know, when you have how do you call that? Breather, it was curved, right? And you blow, it will goes what? Goes straight, right? So if you get a pressure to this tube, this one will goes up. And if this one goes up, this gear go this way. And this gear go this way. So if this gear go this way, the indicator, the pointer go this way. Right? Goes this way. So the indicator pointer goes up. So this is how it works. Okay, so this is from your textbook. Anybody want to tell me PSI? What does PSI stand for? Anybody want to tell me? 0.5 points. It's time to get. You know, I probably will fail 1 out of 3 students in this classroom. But this is the good time to raise your hand to get points. Anybody want to tell me what PSI stand for? Raise your hand. 0.5 points. What is PSI stand for? Anybody? You don't like 0.5 points. You hate 0.5 points. Okay. You lose nothing. Why nobody raise your hand? Yes, please. Yes, sure. Very good. Thank you. Bingo. Congratulations, 0.5. Don't hesitate to answer, okay? Even in Mandarin. Okay, pound per square inch, right? You answer pound per square inch in Chinese, right? Okay, good. Right, okay. So what I want to tell you is that in your midterm exam, tell me what you understand, and I will give you scores. Okay? So this is the answer you need to write down. The Bourdon gauge will be a 1C, the kind of C-type tube, right? And one is open, one is sealed. And when the pressure go in, this one will get straight. And so you can have this sector gear and pinion gear, okay, to do the indication. And the pressure, the range is very good. It's about 0 to 7,000 ATM. Compared to manometer is mercury. It's from 0 to 3. So this is why this is very cheap, but very good gauge to measure the pressure. Okay. So what I want you to give me the answer is draw this picture, okay, and tell me this. Bingo, you get points. Right. So this is the first one. The second one is called manometer. Manometer is kind of, I think you learn this when you are in high school or junior high. So you have you have the fluid here. You have pressure 1 and this pressure 2. So pressure 1 or pressure 2 will be different. So because of the height, you can be able to measure the pressure inside the tube. Okay, so many different types. Because from P1, if you have a long tube, you will have a pressure drop from 1.1 to 0.2. So you got pressure differences between 0.1 and 0.2. So you got P1 and P2. So this is called differential. This is called open end. Open end means that you measure the atmospheric pressure plus the height, and this will be equal to this one, the pressure of this in this point. So this is open end, and this is differential. This is sealed end. Sealed end means what? This is observed. There's no atmospheric pressure. So you have pressure P. You have pressure at the 0.2 here. You have 0.1 here. So you can measure the differences between this one, and then you can get the answer of P1. Okay. Okay. So I'm sure you know this already. So that's no problem. Right. So you have P1 and then fluid 1 equal to P2, fluid 2, and this is called manometer fluid. It can be mercury. It can be methanol, as long as you know the density, right? But all the liquid got the vapor pressure, but mercury is very heavy, so you have less pressure. So and mercury is a very has a high density compared to other liquids. So normally we use mercury. If you use water, this the length will be very high, right? Okay, as long as you know that point A position and point B position equal, and you got a calculation of this, so that will be easy. That's easy. So you use general term. You always use general term, and start to remove some terms. Okay, remove some of the things here. So this is general term. Okay, fluid 1, fluid 2, manometer fluids, something like this. You got P1, P2, blah, blah, and then you got the answer. So differential, because you have differential, all the pressure, if you have a long pipe, you got the pressure drop always from A point to B point. This is called delta P. We call it pressure dropped. Pressure dropped. Okay, so you got the answer. Okay, but assume this one, and then you got this. I don't want to waste your time. Please do the. If you don't understand, you are very welcome to come to me after the lecture. I'll personally tell you how to do this. But I'm sure you understand. This is manometer. Manometer is that blah blah. Okay. So manometer. Okay. This is please. Oh, this is barometer. Barometer is to measure the pressure. Measure the pressure. Atmospheric pressure, because P2 is equal to 0. So barometer is that in a chemical lab or in a physical lab, normally you will have a barometer to tell you what's the pressure at this moment. So you can do a quick calculation. So it's at one open-ended and one seal-ended manometer. This is called barometer. When I was a PhD student, my research is related to pressure, and so every day when I do my experiment, I need to go to this kind of tool to measure the atmospheric pressure, because 760 is a general is an average. So sometimes it will be higher. The atmospheric will be higher. Sometimes it will be lower. We call 高低压, 高气压 or 低气压, right? So because my research is related to the pressure, so every day when I do my experiment, I need to measure the atmospheric pressure using this tool. And it's quite good. This is quite good. Okay, so this is what we call barometer. Barometer. Again, you can use mercury or you can use another fluids. But generally speaking, mercury is a kind of good best candidate to use for the barometer. Right. So example 3.4-3, Yes, I think I don't want to waste your time. So do this by yourself. Right. So the section 3.5 is temperature. Okay. So I think I better stop here because I don't want to stop in the middle, so you don't have a good knowledge to go through this. So, but before we finish the lecture today, I want to tell you that so far we already learned 2 tools. Okay, the first one is called rotameter to measure volumetric flow rate. This is the first one. As a chemical engineer, you need to know this. The first tool to measure the flow rate using rotameter. The second one is to measure the pressure. Use what? Use what? Bourdon gauge, right? Or Bourdon tube. Okay. How about temperature? What do you want? What do you want to use? What kind of tool you want to use to measure temperature? More than 200 Celsius. Well, within 100 Celsius, you might use manometer. You might use thermometer, right? You know, when you want to measure your temperature, your body temperature, you use thermometer. But if I want to measure 200 Celsius, if I want to measure temperature up to go more than 100, you need a special tool. That's what we are going to learn on Wednesday. Okay? Right. That's it for today. I hope you enjoyed the lecture today, and I will see you on Wednesday.